Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's newsletter, well, we're going to take a look at statistical process control. I have a question from someone who says, how often do I sample when I'm using statistical process control in a plating situation? So we're talking about a plating process, and the question is, how often would we take a sample? Once every 15 minutes, once every 30 minutes, once an hour, once a shift? And they're asking me for some advice. And we're going to use that question to answer that question generally, which is, when to sample. This is something that you have to answer the question constantly. When am I going to sample when I'm using SPC? And it doesn't matter whether it's a plating process or any other kind of process. If you're going to use SPC, you've got to answer this particular question. And it's a great question to just show you some techniques and to just show you how to do this generally. So the first thing you need to know before we can answer this, what you have to do, it's very simple really. Take your time, be patient, and understand the process. Okay, so that's what we've got to do. That's how you answer this question. You need to understand the process. So we're going to have a look how the process works, and then once we understand the process, maybe we can answer that question at the top. Okay, now I've got a little component here. So I've got a desktop stapler, which happens, it's my desktop stapler, it happens to be plated, so that's kind of handy. And so we're going to assume that what we're talking about is plating this top cover, and I'm going to use this example of plating the top cover to show you how I would answer the question, certainly in this case, of when would I sample. Now, in most automated plating situations, the components are loaded onto a frame, which they often call a flight bar. So if you imagine this thing, this would probably be something like a meter deep. This might be maybe about 600 millimeters, maybe 700 millimeters wide. It's a frame. There's probably two of them going to go side by side in a plating bath, or side to side that way in the plating bath. And this is sort of the modern way that automated plating processes actually work. So we're going to assume that these parts are loaded onto one of these flight bars, and there's usually a little spring-loaded clip that allows them to be loaded on in a particular pattern onto the flight bar, and it gives a standard amount of surface area to be plated, standard number of components sitting in a standard place in the plating bath. Okay, so we're going to assume that that's the case, and then what we're going to do is we're going to find some data so that we can understand the process, and I'm going to represent the data in a particular way so that I can understand what's going on. So here's what I'm going to do. I'm going to measure some parts. So I'm going to make some parts. So I'm just going to set the process running. I'm going to get the process in its what I consider to be its best condition. So maybe I've just changed the plating, the plating solutions, got them to the correct strength. All the wash tanks are nice and clean. The connection here that the flight bar makes, the electrical connection, they're all nice and clean, so I'm going to get a good electrical connection. So I'm just going to set the plant up, and I'm just going to run it. Okay, so I'm just going to run some product, and then of course I'm going to take some samples. But here's what I'm going to do. I'm going to take a number of samples out of a batch, all right, and I'm going to know that they come from a batch. So in this case, what am I going to do? Well, I'll tell you what I'm going to do. I'm going to take something that I think represents the batch. So I'm going to take the four corners. So this is the sample I'm going to take. The four corners. I'm going to take the 2 in the middle. Okay, so I'm going to take the 4 corners. It's not very obvious what I'm doing there. Let's see if I can make it a bit better. So the 6 that I'm taking off a flight bar. Now I would expect the flight bar to probably have 30 or 40 components on. So the way I've drawn it a little bit smaller in terms of the number of parts that would be on a flight bar, but I would probably take the 4 corners and 1 or 2 from the middle. So this isn't my sample for SPC yet. This is just my sample for understanding the process. And so what I've now got is 6 of these per batch as we plate them. So I would do them batch to batch to batch. And depending on what I think is going to happen in terms of how quickly will the plating process deteriorate. So I'm going to do that, and I might decide to take samples, I'm going to say every 4 hours. And I'm going to do that. I'm making these numbers up a little bit. You would know how quickly you expect the process to deteriorate. So I'm taking these because I expect the quality of the plating solution to deteriorate over 10 days. I don't expect it to deteriorate in the next 10 minutes. If I did, I might take the samples a lot quicker. But in this case, I expect the plating bath to deteriorate as we use it. The solution will get affected. We will be topping the solution up and down, so we will see that natural variability. I've done 4, I've sampled every 4 hours, and I've sampled over 10 days. And I've got 6 per flight bar, 6 per batch that's actually being plated. Now, once I've got these parts, I have equipment and I can check the plating thickness for this particular product. But what I'm not going to do is just randomly put the probe onto this and get a reading randomly across this particular product. What I'm going to do is I'm going to specifically measure it in multiple places, and we're going to make sure that we measure the same multiple places. So often with plating struggles to get inside curves and into corners and things like that. So if you have particular areas that you think the plating process might struggle with, that would definitely be one of the places that you would measure. But I'm going to measure the parts in multiple places. Now I'm going to measure the parts just in 3 places. So I'm just going to suggest I go there, there and there. Now again, you would pick places that you think would show you variability on the part. So what we might be doing is doing 1 this side, 1 the opposite side, and 1 in the middle of the shape, 1 in the cup shape, if you like, because that's where it's going to struggle to plate. So I'm going to do that in 3 places. So for each sample, I have 3 data points. Okay, now then, what I'm going to do is I'm going to put this data on a multivariate chart. Now what a multivariate chart does is this. For each part, it's going to plot those 3 data points. It will plot for me a maximum. It will plot for me the minimum, and it will plot for me the average of the 3. So I'm going to get the maximum, the minimum, and the average. Now there is another video that shows you how to create multivariate charts using Excel functionality. I will leave a link in the comments and the explanation about this video below to that video. So if you've never done a multivariate chart before, it will show you how to do one just using Excel, all right? But you could plot this by hand if you wanted to, the maximum, the minimum, and the average. Now, of course, what I'm going to get is a group for each flight bar. So I'm going to see 6 of these as a group. And I kind of want to understand them as a group. So I'm going to end up with 6: maximum, minimum, and the average. Maximum, minimum, and the average. There's only 5 there. Let's do one more. Whoops. Choose the right colour. The max, the min, and the average. So that's a group. And I'm going to do that for all of this data that I've collected. Now then, what is the multivariate chart going to show me? Well, it's showing me this, look. The length of the line put that right. The length of the line is going to show me on part variability. Now, it is possible that this is variability I can't do anything about because of the design and the shape of the part. That may not be the case, but I want to know what sort of on-part variability have I got. Then what I'll be able to see is the between-part variability. So that is mainly defined by the way the mean is moving up and down there. So I'll be able to see the between part and I'll be able to see the variability. So that's on the flight bar. So that's because you happen to have put the part in the top left hand corner that might not plate as well as parts that go in the bottom right hand corner, or the bottom of this flight bar might plate better than the top of the flight bar, or vice versa. So we're looking for patterns, we're looking to understand the process, and then of course finally I'll understand between group variability, because of course what I'll have, if I can make this felt tip pen work, which I can't, I'll have a separate group over here, max, min, max, min, max, min, etc. And of course that's a group. So you will be able to see between group variability. Now what's happening to all of these, of course, is what you're almost seeing is you're seeing the data cut up into a time frame. So the time frame is instantaneous when the variability is on the part, because instantaneously that part is seeing all of that individual part is seeing all of that process. Of course you're seeing a time frame which is across this flight bar, part to part, and then what you're seeing is flight bar to flight bar, which is what's forming these groups. Now what you're going to see a pattern of change. So what you're looking for is a pattern of change. I don't know where this pattern of change would show up for this particular process, but you're looking for a pattern of change. So the pattern of changes which could be natural to the process. So in other words, the plating solution. If you do not have an automatic way of refreshing the plating solution is getting slightly weaker as you use the process. So you're going to see a pattern of change. It could be that you have temperature control in the plating process, and the temperature control keeps kicking in and out, and so you get sometimes a slightly warmer tank, slightly cooler tank. You're going to see patterns of change. You're going to see patterns of variability, essentially. So another word for the pattern of change is you're going to see the variability. Now, why is all of this important? Because that is how you decide how often to sample. So you're looking for a pattern of change, you're looking for process understanding, and then you set your sampling routine to sort of control that pattern of change. So for example, if what we see is a gradual decline of plating thickness over time, and this period here is related to the plating solution, okay, and there's got to be a point where you say that's the tolerance. Once we get below a certain point, I'm going to need to refresh the solution, and I'm going to need to correct that pattern. Well, if you know that that is happening over let's say it's happening over 2 days, then of course what you would do is you would put in a sampling routine which is inside 2 days, maybe half of that period, maybe a third of that period. Maybe you check it every 4 hours, because you want to see that gradual deterioration of the plating solution. Then you refresh it and you see the process go back to where it was originally set, and now you can see everything, and you're taking the data at a reasonable period so that you don't allow product to be in the deteriorated zone. What we don't want to do is to leave the sampling to here, sample this one, see that there's rejects or product that we're not happy with, then we make the correction, and now what we have to do is to sort, find the defects, replate them, etc. So what we want to do is to see the process deteriorate and be sampling well inside that, so then we can take action and essentially keep the process stable within the original control limits that you set. Okay, so now this is all about process understanding, and of course all of this has gone on prior to collecting data for calculating control limits. Although potentially you could use this data for calculating the control limits, but it is possible that it contains extreme results that actually you wouldn't want to see on your control chart. Therefore, what you'd want to do, collect this data. So here we go. So we would collect the data, do the multivariate, design process control rules. So you might decide as a result of seeing this data that you're going to implement a rule that doesn't exist or change the frequency of a rule. You collect the data, do the multivariate chart, understand the process, design the process control rules, implement the process control rules, then collect SPC data, calc the limits, and set the sampling plan. Now that for me is pretty much what you would do in most situations. Now the multivariate chart, the actual use of the multivariate chart, it's possible that I wouldn't always use a multivariate chart. I might just use a straight line graph. I might just use a straight run chart. But the point about these two is the same. It's to understand the process The multivariate chart in this case lends itself really well to a plating process because you've got on part variability, you've got on flight bar variability, and you've got batch to batch variability, and you need to understand all of this, and then you could set up your rules, and then you could set up your SPC chart. So I've used the multivariate chart because this called for it in a very specific situation, but as a minimum I'd use the run chart. And in all cases what I'm doing is I'm just running the process. I'm taking my hands off. This is really important. I'm taking my hands off so that I can see the process run. Yeah, so I'm not interfering too much. I'm not changing settings on the process. I'm not turning the temperatures up and down and things like that. I'm taking my hands off. I'm being patient. I'm letting the process talk to me. Yeah, give me information and communicate with me. Once I understand the process and I understand its pattern of change, then I can implement some new rules. Then I can set SPC, and because I understand the pattern of change, I can decide how tight the sampling window should be or how wide the sampling window should be. But that is how you decide how to sample in SPC. You get process understanding, and then you use your common sense. And if you do that, and by the way, if you want to make piles of money, this is one of the cheapest ways of making your machinery be at its absolute best. It's not used nearly enough, but if you use SPC and you use it correctly, you can make piles and piles of cash.